I think I don't need to introduce myself because I work here a long time. Everyone here, I don't know everyone. Okay. So today I will talk about the long-term evaluation of the TC rapid identification in Atlantic Ocean. And this talk, we already submit a paper to climate dynamics, so the paper is under review. Okay, the motivation why I want to study TC rapid identification. So for TC study, we have two important issues. One is the TC track. One is TC intensity. So this figure show last few decades improved National Hurricane Center for Hurricane Track. We see from 1970 to 2014, and this is 24 hour, and the green line is 48 hour, yellow line is 3-day forecast. You see that continue improve for hurricane track. However, for the what? I cannot move. Oh, okay. For the hurricane intensity, the figure showed here is that during the last few decades, the curve almost flat, which means improved very, very slow. So the hurricane intensity is a big problem for hurricane research community. This is why that a program, and I think Frank Mark in charge of the national program to study the hurricane intensity.
I just want to point out that that's a little dated, and we don't know the reasons yet, but there have been definite improvements in the forecast filter intensity over the last several years.
Yeah, of course.
And the hurricane model, which was partially developed here, has improved 10 to 15% every year.
Yes. Oh, okay. So in my talk, my focus is on the rapid identification. So-called RI. So RI definition is by Zhang and his co-worker definition is TC intensity increase 15 meters per second over 24 hours. And we know when hurricane wind speed increase, the pressure also decreases. So National Hurricane Center also use RI definition if the pressure drops 42 millibar in over 24 hours, which also called rapid identification. However, in my study, I use the first definition. Okay, we use the wind speed to define RI. And no question about it. RI, as I just mentioned, TC intensification is more difficult to predict, and the RI is even more to predict for the future. So. Question why, like Bob just mentioned that so many models improve. Why the TC intensity forecast error improves so slowly? It's because the TC RI process is so complicated. Here I mentioned several. First one is that TC internal dynamics is also very important. And the second one is small scale change. For example, ocean eddy and atmosphere small scale that many people study this topic. Of course, larger scale like ANSO, global warming can impact the hurricane TC RI. Also, the interaction between the different time scale, TC time scale and the larger scale environment. Today, I focus on larger scale calamity because this is my good part in the calamity part. I focus this part. So this is why I said that what today I talk is not cover everything. It's only this part. Okay. As I said earlier, that a paper published by John at Hurricane Research Division and his co-worker. Here I mentioned two papers here. And he mentioned to me he have a new paper and did not see it. And in this paper, two papers, and John and his co-worker calculated the climatological of RI. And they also use a larger scale climate predictor to calculate the probability of the RI. And here I use 7 as example from his paper. Here is entity and water green shear and the relative humidity and the zonal wind at the 200 millibar example from his paper. However, the long-term variation of I and the relationship with the calamity is not known. This is the purpose of my paper. And today I will introduce what large scale calamity impact this area to this purpose. Okay, so then in order to study long-term variability, you need a data set, right? You need a longer data set. Data set, what I use here is the international best track TC data, which is starting from 1950. And the SLT data, I use the ERST. This is a very popular data set and have a long time, but I also starting from 1950. And ocean data, I use SODA ocean layer analysis field. Atmosphere, I use the 20th century layer analysis field. And the climate index here, including medium 3.4, AMO index, and the NAO index, and the Atlantic warm pool index, also MDR, SLT or not. We'll first take a look. This is not new, okay? You can get it from a John paper. We'll first take, before we move to long-term variability, we take a look at the seasonal variability. And we calculate this result is similar to John paper show. This shows the seasonal variability for I. And top panel show I, low panel show TC number as a function over time. So you see the peak is in the September. This is not a surprise because in September, TC number is larger. The larger TC, you can increase the probability of the I occurrence. And this figure also suggests the larger scale effect, larger scale ocean atmosphere variable for I and TC are similar. So next we take a look at the ocean atmosphere variable during September. This is September case. This panel shows activity. This shows the TC heat potential, and this shows water green shear. This shows relative humidity at 500 millibar. So you see during in September, warm ST is over warm pool region. This region is a warm pool. This is not because warm pool is peaked during in the September. And also during this time, the largest TC heat potential is near the current B and C region. And the water green shear, you see that the low water green shear in tropical North Atlantic and the extension to the West Africa. The humidity also the high value over East tropical North Atlantic and close to the West Africa. So this is a September case. Next, we take a look at the spatial distribution of I. So this we use the last 60 years data make this plot. So what this figure tells us that 3 regions maximum I region. One is over western tropical North Atlantic region, West. Another region is over Gulf of Mexico and the West Current B Sea. And the third region is over open ocean, southeast of Florida. And also there's another, you look at this region, the minimal I region. This is we found this is because this is consistent with the hurricane forecaster call this region hurricane greater. Yeah, why did it happen? This is the physics here. So why the east current is hurricane greater? Yeah. So we should start from this. For the climate people, we know the current is that a low level jet over there. We call this current in low level jet. This figure from my paper in 2007. So we have this shows zonal wind at 925 millibar. Have strong easterly wind over current B. This is called low level jet. Because this is strong low level jet, the atmosphere shows the divergence over the current B and the substance over there. So because this substance, if hurricane move here, this atmospheric condition is not favorable for hurricane intensification, the hurricane decay. This is why we call this region the hurricane graveyard. Next, we move to long-term variability of the ice. And this data show ice time series from 1950 to the 2010. And you see there's no long-term trend, no linear trend. What this means? This suggests, I said this suggestion. That does not mean I prove global warming does not make a contribution to ice distribution in North Atlantic Ocean. For the West Pacific, I forgot to mention, we also have a paper for the West Pacific. West Pacific is a similar situation. Global warming does not make a contribution to the ice distribution. And also this figure, you can see that show interannual and multi-decadal variation for the higher time series.
Quick question.
Okay.
The data set from 1950 to 1974, if you remove 1950 to 1969, do any of your results change? And why did you use 50 to 60?
You can, okay. For example, Peter Weber published a paper in Science in 2012. He started data from 1970. So people can argue, like Chris Lindsay and Stan Goldberg argue, this is not right. You start here, it continue going up, of course, because this AMO from negative to positive. So I understand what you mean. You mean that data is not reliable during early time. However, if we want to study the separated global warming and the multi-decadal variation, your data set must cover at least one cycle of AMO. If you do not, for example, here, you start data here, then obviously it's changing. So this is global warming and multi-decadal variability. So I guess this is AMO synchronous, not
I'm talking more in general, not just the global warming signal. How does the 1950 to 1969 contaminate your results?
For this case, you can see if you plot it from here, it's changed. So I don't know.
I know. I'm not talking about this specific. I'm talking about in general, like you showed the three regions in the Atlantic where there's a maximum. Does 1970 to 2015 show a different result? Because that would be more accurate.
I don't know. I cannot.
Can I interject?
Okay.
It's pretty similar to our paper. We looked at data from, I think, 1989 or so. They look similar as far as the regions. We never looked at what you're looking at as far as trends. And you brought up a good point. You know, if you don't look for a long enough time period, that biases it. But as Tim said, prior to 70, the data is.
Yeah, this is a problem. This is a total problem. If you want to study long-term variability, you need to study. Yeah. This is why we study data from actually hurricane data starting in much earlier than this.
Right.
So this is why I started only from 1950. Long time, if we start a long time ago, then data may be more worse. Yeah. So this is the problem. But the data problem, I did not deal with this issue, and Chris Lindsay is. Deal this issue always. He just published a paper in the Journal Climate, and 1 month ago he argued Peter Weber's result. Its title is Revisit Peter Weber's 2005 paper, and basically they argue Peter Weber is wrong. So I don't know that you guys know that big argument on the TC list community, and yeah. So it's my own personal view about multi-decadal variation and global warming. My personal view is this: you use the data, you cannot do it. You have to use combination of observation and modeling, because data you can just use it. However, if somebody use data and modeling demonstrated, then this would be wonderful. So anyway,
one of the points, prior to 1969 or 70, there were no geostationary satellites, so there's probably more, this is probably an underestimate of that. And I think it even strengthens your argument.
Exactly. Actually, Chris Lancy's paper argued we should start in 1990. Before 1990, data are not good. The Chris Lancy's paper, we should take starting starting 1990 is too short for long-term relation. So that's advantage part and disadvantage part depend on which you want. Okay. So the data are not reliable for long time ago, and however, if you start from here, basically you cannot study the multi-decadal and the global warming time scale. So it's that disadvantage and advantage depend on which you want. Okay. Okay. So based on this time series, I calculated the correlation with the calamity indices. So what I show here is the ANSO index, AM index, NAO, and NAO during winter time, and the MDR and warm pool index. So what we see here is I significant correlation with the ANSO, MDR, and warm pool index, and I also significant correlation with the winter NAO index. However, AMO does not significantly correlate with this surprise, right? I will come back to this issue later. Why the AMO does not significantly correlate with RI? And the top three index is ANSO, warm pool, and the winter NAO index. And we also calculated the correlation of the TC, tropical storm, hurricane, major hurricane with ANSO indices. So what we see here, you see if we take a TC, total TC, then none of these climate index show significant correlation with the TC number. So, however, when TC starting become intensified, becomes tropical storm, hurricane, major hurricane, the correlation becomes significant. What this means? This suggestion is a large scale calamity not critical for TC formation. However, once the tropical depression is formed and continue intensify, then large scale calamity become important. This is the conclusion, implication from this kind of correlation. Okay, then we take a look at the I and ANSO. So the black curve shows the I time series. The red curve shows the median 3.4 index. Top panel shows total, middle panel shows interannual, and low panel shows the multi-decadal variation. We see that correlation, most significant correlation is over interannual time scale. This is not a surprise because ANSO is interannual phenomena, and on the decadal, multi-decadal correlation is not significant.
What is your RI index here? I don't quite understand. What's -3 and positive?
What's negative? Which means when Pacific is air, you're the I.
No, that's El Nino. But what about the RI on the other axis?
I normalize this. It's from this.
Oh, okay.
I normalize. Because I want to compare with the calamity. I normalize it. So okay, the next we show the Atlantic warm pool. Atlantic warm pool is also very important, very interesting. You see that on the interannual time series, the correlation not significant. However, on the multi-decadal time series, significant very high, almost reaches 0.7. So it's a warm pool. And how about AMO? AMO is not significant, no matter what time scale. Total interannual multi-decadal not significant. Correlation is positive, however, not significant. Question is why? You find some correlation, you need to provide some possible cause data. Right? Here I provide in the paper we did not with why. So the AMO does not significant correlation with I, but warm pool does. Why? This is why. The first point I want to make here, we know that AMO is basin-wide activity in North Atlantic. However, the center of the max activity is in high latitude, not in tropical region. So, however, hurricane is formed and developed in tropical region. Okay, and second, warm pool is in the path and birthplace of TC in Atlantic Ocean. And third, warm pool size index we define by activity larger than 25 pound degrees, right? So this kind of index is also an index which weighs the maximum activity where atmospheric convection occurs. So this is very important. This is why warm pool is high correlation with the I. Another point is the large warm pool, small warm pool coincide with warm and cold field of the AMO. So in our another paper we published in 2018, we argued the influence of AMO on TC and climate is slow atmospheric change induced by the Atlantic warm pool. In other words, if your model can predict the AMO, however, your model cannot predict the warm pool, then your climate impact and the hurricane impact in your model still not good, which means warm pool is more important than AMO based on my own study. Okay, so this is some bias. People ask me, okay, you guys study warm pool, you may be biased. Okay, this is maybe this is the case. However, we always argue warm pool is more important than the AMO. The next we take a look at the NAO. This figure shows the NAO compares NAO index and RI index. So again, it shows the correlation is on the multi-decadal time scale. Okay, then we show the spatial pattern of the large scale ocean atmosphere variable. What we did here is regression. Regression of the I onto the activity, TC, heat potential, vertical wind shear, and relative or humidity of the 500 millibar. So the couple point here I want to make here. If we take a look at the activity distribution, you see that the significant by the way, the dot here means above 95 significant level. So significant correlation is over East Caribbean Sea and north of South America. Remember this region I showed you earlier. Here the I is minimal region here. What is suggestion activity not important for I. So this is only suggestion, okay? Second, we take a look at the TC heat potential. We have a strong significant correlation over the MDR region and this region, and the vertical wind shear also shows the strong significant correlation over the MDR region. And for the humidity shows that the significant regression over East tropical North Atlantic. So another point, last point I want to make. Remember, I showed you earlier that the three regions for I maximum, one is over this region, another over Gulf of Mexico, another region over the open ocean southeast Florida. From our calculation for the Gulf of Mexico and the open ocean south of Florida, none of this large scale ocean atmosphere variability is important, which means TC rapidly inhibition in Gulf of Mexico and this region is due to small scale ocean made atmosphere change. The large scale does not play a role for this region and this region. This is our suggestion. Okay. We just here show the most important TC potential and vertical wind shear and humidity is important for the I time series. So we plot time series of the TC potential, vertical wind shear, and relative humidity over MDR region. So you see that all time series are at least the significant correlation with I. And for the TC heat potential and relative humidity shows major show on the interanion time figure. However, for the vertical wind shear, show both interanion and the multi-decadal variation. Then we move to the So we just show that the TC heat potential, vertical wind shear, and humidity is important for the TC interpretation over the tropical MDR region. And here we want to study what impact, climate impact of this largest ocean atmosphere variable. What we first take a look at ANSO impact. So what we did here is a regression of the minimum slip tunnel fall onto the SIT, onto the TC heat potential, onto the vertical wind shear, onto the relative humidity of the 500 millibar. We see that SIT is nothing over there, not significant. And the TC heat potential is only over this region, and some spot area is significant. And for this humidity, almost not significant. The most significant is vertical wind shear over whole MDR region is significant. So which means ANSO impact on the large scale ocean atmosphere variable in Atlantic Ocean is through the vertical wind shear. So question is how ANSO can do that. And from my knowledge, I summarized two ways, ANSO can impact the vertical wind shear over Atlantic Ocean. One is the so-called direct effect. Second is so-called telekinetic. I will introduce both of this. And first, we'll take a look at direct impact. And this slide shows why from David and his former postdoc and worker here. And another paper from me, both paper published in 2002. And what we show here is, to make a composite here, what we show here is that, and velocity potential at 200 millibar and divergent wind. So during the ANSO phase, what we see here, the westerly wind anomaly over tropical North Atlantic Ocean, westerly wind over there. So this westerly wind anomaly ANSO induced westerly wind anomaly over tropical North Atlantic Ocean directly, because in this region, at 200 millibar, the mean wind is westerly wind. So this wind anomaly will increase vertical wind shear, increase westerly wind and increase vertical wind shear for the ANSO. This is direct effect. There's also another mechanism, so-called teleconnection. People maybe know this figure because this is published a long time ago, and this is in UW, very nice and very good scientist published the paper in 1981. It's a classic paper in class textbooks. So what this paper is, when Pacific Ocean, we have the El Nino year, the ocean is warm here. The rainfall increase over central Pacific, and this rainfall will induce atmosphere wave train, which is so-called in the subtropical region that's high pressure. That's not Pacific is low pressure. Over North American we have a high pressure. Most important this one, over southeast U.S. and the Gulf of Mexico, we have a lower there. This low pressure at 200 millibar will produce westerly wind over tropical North Atlantic. And this westerly wind anomaly will increase upper level mean wind. So the vertical wind shear increase. So this is so-called teleconnection. The both work together ANSO induce the vertical wind shear over the tropical North Atlantic region. Now Wang pool, next we take a look at how Wang pool change atmosphere ocean atmosphere variable. What we did here again is the regression. Regression of the Atlantic Wang pool onto the SIT, TC heat potential, vertical wind shear, and the humidity. So what we see here is a significant correlation or regression over this region, and the TC heat potential also shows significant regression, and vertical wind shear is also this is. Remember the figure I showed you earlier. You can remember this is similar to the regression, which means Atlantic warm pool is very important for eye distribution. And this correlation, right? We need to study physics. Why warm pool induces this kind of change? For the SLT heat potential, it's very easy to understand. When warm pool is larger, ocean temperature is increased. The upper layer ocean temperature also increased, so significant positive correlation. For the humidity also, when warm pool is larger, atmosphere moisture is converging, right? Converging produces high humidity over 500 millibar. So this is very easy to understand. The question is this, physically for this, why Atlantic warm pool reduce water wind shear over MDR region? So this is a mechanism. Actually, we published this paper in 2008. This is an older paper. We use a model, and with Santi and David, I believe Chris Lassie also co-authored this paper. What we did, we performed numerical model on large warm pool, small warm pool. And what we show here is the difference between the large warm pool and small warm pool model on. So what we show here is the temperature height and the wind at 200 millibar and 850 millibar. So at a low atmosphere, we show the cyclone over there. And upper level show anti-cyclone. And this anti-cyclone will induce easterly wind anomaly, because the mean state over here is a westerly wind anomaly. So this easterly wind anomaly will reduce the mean state. So the water wind shear will reduce. The similar situation for the lower level. Lower level, we have a cyclone here, right? The over tropical North Atlantic Ocean has a westerly wind anomaly. However, due low atmosphere, we have east trade wind. So this westerly wind anomaly also reduce east trade wind. So net result is large warm pool reduce water wind shear in the MDR region. This is the physics. And also this is based on the Gill 1980 paper, which show in ocean, in tropical region, if you put heating air there, atmosphere is from the bar clinic, which means low level, upper level is opposite. So this paper is very important for the ocean atmosphere interaction. Actually, without this paper, our understanding of the climate and the ocean interaction may be delayed many years. So this is a very important paper, and I guess every student in the graduate school study with this model. It's an analytical model. You put the heating over there, you get a solution. Atmosphere is curving wave loss field. It's a very nice paper. When I was in graduate school, I read the paper. I thought this person very smart. He's very analytical. You put the heating over there, you get solution. So it's very, very nice. You have the least negative. But this, he passed away a long time ago, okay? Then we take a look at the NAO index. NAO index on the largest scale ocean atmosphere variable. And again, the regression was the NAO index on SIT, TC heat potential, water wind shear, and humidity. So we see the SIT impact is significant over west MDR region, and also heat potential also significant regression over this region. And for water wind shear, it's almost not significant over MDR region. And for the humidity, that this part, there's significant correlation. So the question is why NAO can produce such kind of ocean atmosphere change. So the physics also very simple. I believe this figure, from David, and we published this paper, I believe, in 2006 with Santi, David, and David's leading author for this paper. What we did here is we make a composite for the positive NAO and negative NAO. What we show here, the color is jet potential height, and the vector is wind. So we will see that the high pressure here and low pressure in high altitude, and this kind of atmosphere induce strong easterly wind anomaly, which increase trade wind, and this trade wind induce the SLT, that then ocean atmosphere interaction feedback process continue maintain the SLT and the wind pattern to the hurricane season. This is why winter can influence the summer and the fall hurricane season ocean atmosphere variable. Basically, this was a summary. So in our paper, we find 3 regions, and I is maximum. One is over West Tropical North Atlantic, one is over Gulf of Mexico and West Caribbean Sea, and another over the open ocean southeast of Florida. We also find a minimum area region over East Caribbean Sea, north of South America. The second conclusion, and based on our study, if you believe the delta level, the global warming does not make contribution to RA, okay? RA for based on our study. Of course, when we publish the paper, people will argue, okay, your data not good, and then this conclusion not right. Okay, fine. But at least, so far is we based on this observation from 1950, we get this conclusion. So this is, and top 3 index, very important index is the ANSO index, Atlantic warm pool, and AO index. And for the ocean, SAT is not important, okay? So if you want to study RA, then SAT is forgot about SAT. So it's water wind shear, but not very sure. TC heat potential, I mean up there process is very important for the RA, okay? And water wind shear, atmosphere water wind shear is also important. And the humidity is important in East Tropical North Atlantic. Over there is important. For west part, not important. And another, I showed that okay, this conclusion is over MDR region. That I showed earlier. That also another 2 regions. One is over Gulf of Mexico, another is over open ocean southeast Florida. And our study suggests these 2 regions, large scale ocean atmosphere variable is not important. So the hurricane intensify, like the intensity over there must control by small scale change. For example, ocean eddy or hurricane internal dynamics. So large scale not play role over there. And final conclusion, I think that this is also important. So our result suggestion large scale calamity is not critical for TC formation. However, once a tropical depression is formed over ocean, then large scale calamity will play a role. So this conclusion is also very important, also physically makes sense because tropical depression is formed requires a small scale disturbance. For example, West African east wave can induce the tropical depression, and a small scale volatility also important. So this conclusion, when I get this I got a revert back. One of the revert like this conclusion is physically is very reasonable, and also the data analysis suggested this. So this is, I stop here. If you have a question, we can discuss. So anyway, this topic is a very good topic. I like to continue work on, but right now I work on the Atlantic Ocean. I also work on the West Pacific, and the East Pacific I did not do that. So thank you. Wow.
Very interesting study. You looked at the number of RI events here. Do you plan on looking at the intensity of RI events? For example,
you mean based on major hurricane, hurricane?
Such as the kind of intensification that occurred with Hurricane Patricia in the Pacific, but there's no climatic trend that you're seeing with regard to the numbers, but what about how strong the RI is?
Oh, you mean the rate versus regular RI?
Yes.
Regular regular RI, right?
It may be another way to take the research.
Yeah, it is true. Our conclusion, all the conclusion here depend on our definition of the RI here. RI is we define a TC intended increase 15.4 meters per second over 1D. So that John's work on this about all the other definition, right? At least in your paper you show 3 definitions. But here I use this one for the other. I don't think that the bigger conclusion will change, but a small correlation. The correlation maybe have a small variation.
You have a hard time going back in time and
Yeah.
trying to say that you could tell if there was a 90 knot increase in 1960. I think that's the issue with the RI part. That I think Tim's point is well taken. I think there's no way. You can't have it both ways. You have to look at the whole trend. You have to look back further, but it's very difficult to tell what the intensity change is in a 24-hour period without satellite data. So I think that part is kind of, pretty uncertain. So I would think it would be nice to look at more recent period, even like the mid-80s now, to see if you see similar trends. Obviously, you can't go back as far as
Yeah, of course. Delta has a problem. Yeah, Delta has a problem. Even not hurricane Delta, even the ocean. I use here soda. Okay, I make assumption here. You need to believe soda is right. However, soda is a problem. Jim Carter is my friend. I don't want to encourage people use it. However, we have no choice. If you don't use soda, what do you want to use for long time later? The soda Delta over the warm pollution not good. Okay, so it's because the observation over there is a very small number of observations, so it's totally depends on model. They're not good. So the main assumption for the conclusion, you have first assumption you believe your Delta is right. Both ocean and water Delta is right. However, that's not true. Soda is not reliable in warm pollution.
It's also a lot harder to determine whether you've got an extreme event in RI versus an ordinary one without aircraft being in the storm at the time.
Yeah.
And because of the short duration of the airplane flight, you don't always catch it with the reconnaissance. That will shrink your sample size quite a lot if you try to do that.
Yeah, actually, Delta is always, like you said, the hurricane Delta is actually, I do not work on Delta data. The Chris Lancy worked on the Delta, and he got some funding from the CPU to look at the hurricane Delta go back early time. And I think he confident to me his funding is finished. He cannot no longer work on. I think you use base money to work on. It's a hardly similar problem from scientists studies tornado. Tornado Delta is a big problem, even worse than the hurricane. So that because the observation during early time is not reliable. So, but we have to use our current knowledge to show what it is. You have, for example, conclusion I got here, you have to believe the Delta is reliable during early time. Otherwise, the conclusion is garbage. So we have no choice right now. Yeah. This is better Delta. I can use it. Yeah.
Yeah, interesting work. This work is, of course, predicated on the assumption that the large-scale environment really controls RI to a large extent, which no doubt it plays a significant role. However, there is at least massive research at HRD that also is looking at the intercore dynamics and the extent to which those dynamics may modulate the likelihood of rapid intensification, perhaps even allowing us to identify situations where a storm, given a favorable environment, will or will not undergo RI. Your fifth bullet is really interesting to me because that seems to suggest that there is a way that you can quantify the extent to which large-scale environment versus intercore dynamics may play different roles. Let me ask a question. Okay. In terms of the likelihood of RI.
Yeah.
How did you? I guess maybe I missed it in the talk. I apologize. But how did you do that? I mean, you're suggesting a regional variation and perhaps a variation as a function of NTO phase or AMO phase or things like that. It's just I'd be interested in
this conclusion.
Yeah.
This conclusion I got is from my regression calculation. We show I in this population in Gulf of Mexico and open ocean South Florida showed non-significant for large scale variable SST, TC potential, and water green share and humidity. I also analyzed the volatility. I did not show in talk because it's not result not good. The large scale in this population not significant. So which imply other process. For example, at least in the beginning of my talk, the I process control include many processes.
Yeah, right.
TI internal dynamic, small scale like warm eddy, cold eddy in the ocean, and large scale, and that's what I focus on here. Also, there's another topic, the interaction between the TC dynamic and environment. This is also another topic. So it's which means the other process may be important. So for this population.
Can I just follow up on what Ralph said? I mean, I totally agree. I think that the reason you're saying, well, I don't know for certain, but there's a lot of variability environmentally as far as, you know, how favorable conditions are. If they're extremely favorable, it makes the intercore processes a little less critical. And if they're marginal, it makes it a lot more. So I think in the case of Patricia, the environment is very, very favorable, and the probabilities were very high that rather than escapement curve, just doing it at a large scale. However, the likelihood of getting conditions like that very often is pretty limited. So most of the time it's kind of in the middle, which in those areas a lot of times it is. It's kind of marginal. So that's when the intercore plays more and more of a role. I mean, regardless of where they are, I'm guessing, I looked at that a little bit as far as predictability. In those two areas, it's probably, they're kind of, you can go either way, which means the intercore is kind of good.
Yeah, this is the only implication from our study. So detail, I don't know. Maybe something else, maybe, so who knows?
Well, and I can get into the ENSO phase, for example, because the NDR is here with the radar NDR.
Yeah.
So, and that's just because it's such a strong ENSO event. That would maybe suggest that the intercore might have more role.
Same first.
I just wanted to add to this point. I think, correct me if I'm wrong, I think what you're trying to say in that second to last point is that variability of the SST and the other factors is not a factor in that area. Not that the SST itself is not a factor in that area, it's the variability, and that it maybe in those regions you don't have the variability, and I think some of it might be a difference in what climate scientists are calling small scale and what meteorologists are calling small scale, because you included in that small scale the environmental impact, which includes the shear in the area, includes the SST in the area, and the ocean heat content, as you said. So I don't think he's saying that it's the intercore dynamics in that area that's important. It's just what's going on around the TC, the near environment, and it's not the climate factor, because there isn't that.
Yeah, the climate from analysis here, you believe data is the level here. What we show here is something else, not large scale climate.
Right. Okay. So I understood what you meant.
So it gives you the near.
David, you have a question?
Yeah. At first blush, the surprising thing in all of this is that you see the high correlation with the NAO in the winter. Not the summer, but the winter. Not contemporaneous with the TC season. And I think what we're seeing there that's different with the other indices. The other indices are ocean-based indices that immediately affect the atmosphere. And so you see the relationship with the summer ocean indices. Of course, you showed for the total indices, but I'm sure that it's the summer.
Yeah, other word for summer. Yeah, David's question is very good. Actually, when I make this calculation, it took me 2 months to figure out why the summer AAO index does not correlate with this and the winter. So that time delay over there. So what I cannot solve the problem until 2 months later. I thought, maybe we argue I'm not sure this is true or not. What my argument here, why the winter? Because AAO is chaotic. It's atmosphere phenomenon. Okay, we know that. Not like energy with the ocean atmosphere interaction. AAO is atmosphere, pure atmosphere phenomenon. The atmosphere energy is stronger during winter time. This is why AAO is stronger in winter. Now, next question you need to ask, why your winter can influence summer or fall hurricane season? So what my interpretation in the paper, actually, the reviewer also agrees is we argue during winter time, NAA will change tropical acidity and wind. Okay, I show over there. Then this initial change acidity wind, then maintained by ocean atmosphere feedback, like a west feedback proposed by Xiangqing and our feedback about long wave radiation. This local feedback continue this initial acidity and wind, then go to the summer. This is our interpretation. So until I figure out this, then I submit the paper to the journal. Otherwise, I have 2 months trouble for me, the winter time and the summer time. So this is a big question.
But I think what that is also telling us is that, yes, if the NAO is affecting the summer through its effect on the ocean during the winter-spring period.
Mm-hmm.
So if you have an NAO of a particular sign in winter-spring, that leads to a large warm pool or a small warm pool, depending on the sign. But it also suggests that the relationship with the NAO is not independent of the relationship
exactly.
with the AWP.
Yeah. It actually in the paper, in this kind of session, argue, okay, you have a 3 index here, and to 1 pool AA. All they are not independent. They are dependent on each other. So you, from observation, you can do is you do the partial correlation. You can do, but the best study is use the numerical model. You really move answer and perform model long and take a look at the warm pool. Similar, if you want to study the AAO and warm pool impact, you perform the model. This is the advantage part of how numerical model study. So from pure observation study, it's hard to separate because they're independent. The only possibility is the partial correlation, and also partial correlation. I do not totally believe the partial correlation.
I have a question on one of the figures you talk about the warm core and warm pool and the MDR.
Uh-huh.
So in the figure you showed that the highest duration, I think for the shear, for the warm pool, for SST, and also for the ocean heat differential, it's co-located, but for the relative humidity is actually located near the near the effort. So hopefully same is even.
Yeah, this is over this region. The humidity is significant over this region. Here is also significant. This is 95. This is 99 significant. In this region also is significant. But not largest significant over this region. Yeah.
So what's the possible reason why the other 3 variables, the peak is located at the middle of the
this is also a good question. The answer I don't know, but it's possible. When you have a large warm pool here, warm pool larger, the warm pool extends eastward. So the atmosphere convergence is over a whole tropical North Atlantic, and this region may be climatological relative humidity is larger. So this is why maybe
there's a lot more variability in the humidity further east and further west. So that could be why.
Yeah.
Say something about the strength of the air.
Yeah.
I think that's the variability. I agree with Sam.
And you're implying effects that the Atlantic warm pool is causing? It's affecting the variation? Related to it? I mean,
yeah,
it's a tricky thing.
for the shear, it is here. Shear, we use the new American model demonstrate shear is induced by a large warm pool small wormhole value. For the humidity, we did not do it. I believe we do the atmospheric tip, the atmospheric convection. We did that, and with Sankey and David, we published paper. We showed the tip, but it's not in this region. Over here, I believe wormhole larger atmospheric tip is increased over this. It's not this region. So this I don't know. Okay, so
That's probably clear.
yeah. Okay, thank you for coming.
Because for the 20, I think by you will have